Let's go to lab. We are getting late. Let's go. Hey guys, what are we doing today?
We're doing the separation of hydrocarbons, fractional distillation.
Are you gonna join?
Sure. Come on, guys.
Come on, let me show you how to do it.
All right.
Do you know what fractional distillation is all about?
No?
Alright. Distillation has been used to separate the components of mixtures. For a long time ago, the Egyptians used it to distill wood to make and balance fluids. Right? And then today they use it for a lot of things, like to make perfumes, to make flavors, to make colorings, and then the most important thing, they use it for the refining of petroleum, which is to produce fuels, lubricants, and petrochemicals.
What this fractionation column does is we have cyclohexane toluene mixture is going to rise up to the rise up through the beads, and we're going to run the water out of the faucet, which is going to come into this tube, and it's going to cause it to condense up here. So basically, what we're doing is we're separating the cyclohexane from the toluene, since it has a lower boiling point. We're going to turn on the heat to the element, and we're going to crank it up to about 150. The reason we're going to go up to 150 is we want the solution to get to a boiling point between 78 degrees Celsius or 81 degrees, because that's when we're going to start seeing our solution start to condense, and we're going to get our first few drops. While this is starting to heat up, we're going to wrap the column with aluminum foil, and the reason we're doing this is because it's going to keep the heat in, and it's going to allow the solution to heat up faster.
Take it out.
If you can look at the fractional columns here, you see how they look really wet, because you'll see condensation coming down the columns and dripping down the side of the tube, and what it does is basically dripping down back into the flask. So this is the toluene coming back into the mixture, and the cyclohexane is up here. You'll see it in the gas form, which is going to start condensating in this tube, and you're going to start seeing some drops come off of this pretty soon. But the temperature's starting to go up. So we're at almost 60 degrees right now, so around 78 or 81 degrees, somewhere in there, we're going to start seeing our first couple drops.
So right now, we're going to go weigh the vial, right? This little thing, we're going to go weigh it over there, so we can find out when we get the cyclohexane, and then we support it with the graph.
So what we're looking to see is basically the first 5 drops, the HUBT, is going to be mostly cyclohexane.
7.234. We get the cyclohexane, and we put it here, then we can find the density with that. And each different volume, we're going to write the temperature that we're going to get.
All right, next we're actually we have the vial of the first HETP, so we're going to get a mass spectroscopy to compare it and contrast to the other 4. We want 5 vials. It takes about 25 to 30 minutes. It's kind of a long process. So what we can do, special, we can actually fast forward in the future. We favor having the remote control. That's 25 times divided by, of course, it's not working properly. It's not working, I don't know. You know what? Old school, Wayne and Garth, future. Here we go. Whoa! Future us. This is future us. 25 minutes. You look good, bro. You look good, man. 25 minutes. So we got file number 5.
So now that we're in the future, I really don't have to write nothing else because my old me wrote it for me.
Of course.
So,
brilliant.
As you can see on the HCP, the first 5 drops is 68 degrees Celsius. Second vial at 10 milliliters, 72, 20, 79, 30, 94, and guess what? At 30 and at 40, we stay at 94.
You see this huge peak right here, that's your cyclohexane. This small peak behind it, it's going to be your toluene. So there's a high concentration in the first 5 drops of cyclohexane as compared to toluene. But as you go from graph to graph, you see in the next one that the toluene peak is getting bigger. And if you go to the 3rd vial, it's going to get even bigger. And then you go to the 4th vial, this right here is your cyclohexane, and now you're with nothing but toluene. So this is the vial taken at 40 mLs. We see the area ratio. This is the cyclohexane on top, the toluene on bottom. We see how the number is very small. So we get 0.0064375. So we're going to plug that number again into the mole ratio formula that we had. So this is 0.00643 cyclohexane over 1 toluene. We use the conversion factors of the molecular weight of toluene over the molecular weight of cyclohexane, and then multiply the conversion factor of 1.1 cyclohexane over 1.05 toluene. We come out with a mole ratio of 0.007439 cyclohexane to 1 toluene. Now if we plug these into the mole fraction equations, so cyclohexane's here on the left, toluene's on the right, we see we get a very, very small number for cyclohexane and we get a very large number for toluene. And remember, the closer the number is to 1, the larger the value is. So this is exactly what we expected to happen. So as the distillation took out the cyclohexane in the beginning, and all we were left with is toluene at the end.